back. And so what I want you to remember is that the Commission has a website. If you are interested in the area, just register on the website. You get either the option to just give us your email address, or actually register as a user of the website, which allows you to post news and get everything that we post on the website. So if you are interested in the area of research and computing, that's a good way to get resources. And now I'm glad to introduce Edgar. Here you have a selection of products in his work, and I'll leave it to him. 30 minutes, I'll give you 5 minutes. Fine.
All right, thank you very much. I'm going to start with my favorite words. So I'm going to talk about pluralism before I give you the very big picture. And I'm going to illustrate pluralism by a small case study. If you have a good look at Marvin Minsky's 1967 book entitled Computation, Finite and Infinite Machines, and you don't wear your computer science glasses, but your epistemological glasses, then you will observe that the word program in the first half of the book refers to data and instructions that fit in a real, finitely large memory of a physical computer. In the second half of the book, on page 153, the same word program refers to a mathematical object of unlimited storage capacity. This is a very small example of pluralism, where you see that the word program has a different meaning, in this case by the same author in one and the same book, and that's just an observation, and so far I don't think that's so surprising. But the word program has acquired several meanings throughout the history of computer science, across the writings of several actors. So actor A could be David Parnas, who today still uses the word program to denote a technological artifact. And I will give later on, at the end of my talk, I will show you a dialogue between Parnas and some other top researchers in computer science, and you'll see that Parnas uses the word program in this way, while the people who he's communicating with use it in a different way. So there's a mismatch in communication. Actors B and C can be Edgar Dijkstra in 1973 and Christopher Strachey in 1973, who used the word program to refer to a mathematical object, but for Dijkstra it's a finite size object. For Strachey it's actually a Turing machine program. And I will delve into this example later, in some 10 minutes from now. Actor D can be the Dane Peter Nauer, Michael Jackson, or the philosopher of computer science Brian Campbell Smith, who say that a program is not a logical mathematical construction, but a model that cannot be understood by solely resorting to logic and strict rules. I'm not going to delve into this last part, but I have interviewed Peter Nauer, and one of my books is an interview with Nauer. And interview with Michael Jackson is coming out next month as well. My research objective is to contrast a particular computing concept, such as the word program, from the viewpoints of multiple actors. That's what I do as a living, and I try to do this exercise for several concepts, not just the word program, but also the words recursive procedure. I have published about that. Computer science interview with Knut is on this topic, and today also, to some extent, I'm going to talk about the words Turing completeness and what did that mean for different actors, even though as a historian then I will be looking at the 50s and 60s when that word was not yet being used, but they were intellectually talking about such things. So I have to be a bit careful, and I can imagine that the historians, the professional historians, will perhaps frown a little bit, because I'm well aware that I'm actually today primarily putting on my computer science hat. I would like to do this exercise the coming years so that we gradually acquire a better understanding of the constituents of present-day software. And pluralism is not only a word that I embrace, but several researchers, and Matti Teter's book is very pluralistic. You have different angles of looking at the question, what is computer science? And the way I read Turner's work is also like this, and it's certainly also Mackenzie's book, which is has for a long time been my most favorite book. So today it's about, is C a Turing complete language? And I will primarily address this from a historical angle, so this is the left part, and only a little bit from a philosophical angle. So I'm not going to give the complete story. I'm primarily inspired by the philosopher Brian Smith, his seminal 1985 paper, which is entitled The Limits of Correctness. In that paper he introduces a world model relation. You have the real world containing technological artifacts, and then you have a model of a real world, and his main takeaway message is that any mathematical model you would choose will always be imperfect in one or more ways compared to whatever you're modeling in the real world. And my master student of mine gave a very good example in her essay based on apples and strawberries. In the real world we have apples and strawberries. You could mathematically model that. You have green apples, so you can model that with green, and red strawberries, you can model that with the attribute red. And then you have a mathematical model. You can write a program, and if in your program you can differentiate between red and green, then at least with respect to your model you can prove that your program is correct. But you cannot prove that your program is correct to the real world, to your design intent, the informal real world, because guess what? We also have red apples in the world. So our model is limited. Of course you can enhance your model, but the point is every time you do that your model will be imperfect in one or more ways. Now this is a really beautiful paper, and inspired by that I'm today going to talk about a slightly different relation, what I call the programming model relation. And programming refers to industrial programs and industrial programming languages such as C, Java, Haskell. And then the model refers to the mathematical counterparts of those technological artifacts. So I'm going to talk about operational semantics, formal syntax, etc. That's the mathematics. That relation is the key thread throughout this talk. Industrial programs versus mathematical programs. If you talk to Dave Parnas, a program is primarily an industrial program. If you talk to Dijkstra, if he were still around, it would be a mathematical program. I realize that this is an oversimplification, but that's basically my point. If you look at the language manual of the industrial programming language C, for example, you will notice that the syntax is rather well formalized, and that hasn't been a problem since the advent of Backus-Naur form notation in 1959. But formalizing the semantics of a programming language remains a problem up till this day in computer science. And so a lot of the meanings are expressed in English, in natural language. And then if you visit different computer science departments across the world, you'll see different computer scientists, different mathematical modelers model or present a formal semantics based on the language manual in different ways. They each have their favorite formalism based on different abstractions. So we will see examples in a moment where Dijkstra does embrace the first abstraction, which allows one to express arbitrary large positive integers, but he does not embrace the second one, which would allow for representing infinite precision real numbers in his model. While somebody like Christopher Strachey in that same year, 1973, did embrace both abstractions. So this is again a little example of pluralism, different people modeling the same technology in different ways. And it is actually related to the big question, is C a Turing complete language, which I will not address because I would need to talk a lot more about philosophy. And let me just tell you this as a teaser, there are philosophers who claim that several researchers, and I was one of those, there are several researchers who merely assert that the industrial programming languages X, Y, and Z are Turing complete, and then they use the alleged Turing completeness of that industrial language to end up with an impossibility theorem about programming practice, and so there are philosophers who claim that this reasoning is flawed. And that's all I'm going to say about this today. And so that the question, is C a Turing complete language, actually contains a category mistake and is ill-posed. Starting with lots of historical case studies, let's go back to Minsky's 1967 book. And what did a program mean according to Minsky? Well, I'm going to quote him. The black words are from him. But before I do so, let me ask you, do you think about this question. Does a program here refer to a mathematical program, a mathematical object? Or does it refer to an industrial program? And I know that I have not yet really explained a lot about the difference between these two things. It's going to become clearer later on. Or is he just conflating the two, or is there no need to distinguish between the two? Okay. So here I go. He says that the unsolvability of the halting problem can be similarly demonstrated for any computation system rather than just Turing machines, which can suitably manipulate data and interpret them as instructions. In particular, it is impossible to devise a uniform procedure or program which can look at any program and decide whether or not that program will ever terminate. Now, I asked you a question, but I'm going to just give my own interpretation now, based on an entire reading of the whole book. In this part of the book, I take his words to mean that a program leans towards the second interpretation, that is primarily a mathematical program, if we would have to make a choice. Because in the first paragraph, he wants to now step away from just looking at Turing machines. He wants to make a claim about computing practice, and I think that the follow-up excerpt also supports my interpretation. He says this observation holds only for programs in computers, but with essentially unlimited secondary storage, since otherwise the computer is a finite state machine, and then the halting problem is in fact solvable.
In principle.
Sorry? No, I'm curious now.
No, I said at least in principle.
Yeah, at least in principle. So my interpretation of Minsky, once again based on more than just those 3 paragraphs, is that if we view industrial programs as Turing machines, if we model industrial programs, things that are embedded in a laptop, as Turing machines, then we have an impossibility result with severe practical implications. And he's by no means the only one who has made claims like that. Let me already just indicate that if you have a mathematical model, you cannot destroy it, but if you have an industrial program embedded in my laptop, and I just burn my laptop, then that's gone, but the mathematical model remains. This is the kind of philosophical distinction I get from the literature, and I will try to articulate that a bit better in a moment. Now, Minsky's reasoning is only valid if industrial programs can only be adequately modeled with Turing-complete formalisms, and thus not say as linear bounded automata, push-down stacks, push-down automata, finite state machines, etc., etc. In fact, the whole book is about all these different models of computation, but he doesn't often use the word model. I'm, in my presentation, explicitly distinguishing between the artifact and the model, a la Brian Cantwell-Smith in 1985. Now, if all of this reasoning is correct, we can already look at findings published by Mahoney and myself that computer scientists abstracted away from actual computers in the 60s, 70s, 80s, etc. in diverse ways, and many did not resort to the Turing machine model or any other Turing equivalent model. And there never has been a standard model of computation. It is the quest for such a model that brought computer scientists together. And I'm going to support these 3 messages with new historical findings, which are about to be published. And I hope you can appreciate now the historical part of the talk, even though you may have questions about what I just said earlier. The historical mini-tour, I'm going to start by fixing my terminology, which is again a bit a historical thing to do, but I'm going to look at Martin Davis's 1994 textbook where he introduces notions such as algorithm, partially computable function. I'm going to fix that, and then I'm going to go to the 50s and 60s, look at the Fortran translation system. How did people model Fortran? How did they mathematically model those industrial programs? What about Algol? And what about Strachey and Dijkstra in the 70s? And then a little bit about model checking. And the whole point of this mini tour is again pluralism. Different actors did things differently, even though most of them had a mathematical agenda, as Matti Teter also referred to in his talk. So this is an authoritative textbook, Martin Davis and two authors, where you get, where he explains that an algorithm is an informal concept. Language in his book refers to a well-defined object, a mathematical object. In fact, in the second chapter, he completely defines his little programming language L with a formal syntax and a semantics, etc. He defines a partially computable function. He does not use the word Turing complete in his book, so I'm going to give you the definition of Turing completeness in a moment based on another article, but there is no problem here. I think he would agree with the definition. Graphically, I would summarize a large part of his book as follows, using Brian Cantwell-Smith's glasses. We have programs written in Martin Davis's L programming language, and he gives a meaning to each kind of instruction. And he also, and this is by no means a surprise, I guess, each of these programs in his language correspond with a partially computable function, and in any partially computable function you can think of, you can express in Martin Davis's L programming language. Brian Cantwell-Smith, I assume, would agree with me that these are actually mathematical models of an industrial program, for example a C program running on my laptop. Again, I can destroy that, but these are pure symbolic things. Abstract things is perhaps the better word. Martin Davis also presents an operational semantics of his language, using the formal syntax of L, introducing a mathematical notion of state and snapshot, etc. And that actually is, what he's actually doing is modeling actual computation. Davis says that a partial function is partially computable if it is computable by some L program. And then this definition comes from Jeroen Voeten's paper. A Turing-complete language is a formal language that is able to express all partially computable functions. So that was just to fix the terminology. Let's now go to the 60s primarily. Meyer and Ritchie introduced their loop programming language, their loop formalism, to mathematically model Fortran programs. So this is one source I'm relying on, and this is, if you like, what we would today call the language manual in 1954 of a very early version of the formula, the Fortran system. Graphically, I would summarize Meyer and Ritchie's paper as follows. They explicitly talk in their introduction and conclusion about real systems and Fortran programs. Most of the body of the paper is about their formalism, a loop program, and every loop program corresponds to a primitive recursive function and vice versa. So this is a non-Turing complete formalism that they chose to model Fortran programs. Now they say things about unsolvability as well, but that's the topic I will not address today. That's the second part, perhaps a bit more controversial part of my talk. Meyer and Ritchie, just like Martin Davis, introduce a mathematical state which captures specific values of variables. And just like Martin Davis, they embrace abstraction HaPoC, which is that you can represent arbitrarily large integers in your formalism, in your loop programs. Just like Martin Davis could do that in his L programming language. Just like Martin Davis, they do not accept abstraction AR, that you can represent infinitely large real numbers. So the big difference then between the two formalisms is once again that Meyer and Ritchie have chosen a non-Turing complete formalism. And that makes a lot of sense, because if we now go look at the language manual and we go look at actual computing programming practice with regard to Fortran, you'll see that Fortran designers had eschewed unrestricted forms of recursion. And in fact, ALGOL 60 and Lisp were the first languages to actually embrace recursion. And I've published about this, I'm not going to say more. But you could then ask the question, okay, we're not going for a Turing complete language, let's go for a non-Turing complete formalism. But why did they choose primitive recursive functions? I mean, you could take, there are many other non-Turing complete formalisms. Well, you can especially ask this question if you observe in the language manual that Fortran variables had fixed machine-dependent bounds. So you couldn't represent an arbitrarily large integer, according to what was written in the language manual. Fortran was only designed to work for IBM machines, nothing else. And the real capacity of the machine, that number, was put in the language manual, 10 to the power something, but you couldn't write integers larger than that in your Fortran notation. It was not possible to represent arbitrarily large integers and reals in Fortran programs. So that's already a bit of pluralism. We have Martin Davis using a Turing complete language, Marian Ricci using a non-Turing complete formalism. But let's become a bit more historical and let's try not to refer to Martin Davis, who wrote a book in 1994 while we're actually talking about the 50s and 60s. So let's go to ALGOL in the 60s. The language manual written by Peter Nauer is one of my sources. This is a paper by Adriaan van Wijngaarden about ALGOL 60, and I'm also referring to my own book. ALGOL 60 was primarily a tool for numerical analysis, and it was renowned for recursion. It was possible to express potentially unbounded forms of recursion, and the idea was that then the runtime system would have to raise an error if the computation got out of hand. But this was a novel idea, this recursion. Now we take it for granted. Now, just like with Fortran, abstraction AR was not admitted in the ALGOL 60 language manual. Unlike Fortran, specific machine bounds were deliberately not mentioned in the language manual. ALGOL 60 was intended to be a machine-independent language. It was not supposed to only work for IBM machines. The whole idea was to, and this is the political story, to get away from this IBM monopoly. So there were no specific machine bounds. And this is what Peter Nauer said about this issue. Numbers and variables of type real should be interpreted in the sense of numerical analysis, and specifically as entities defined inherently with only a finite accuracy. So even though there were no machine bounds in the language manual, they did not abstract away from the finiteness of real computers. This is very important. And Van Wijngaarden said something very similar, and that's exactly because they were both numerical analysts. He said the following: of course, on the one hand, the concept with which numerical analysis deals can all be considered as approximations to concepts in pure mathematics, the real arithmetic. But then he says something similar to Nauer. However, the numerical analyst might also consider the result of the computation to be the thing that he wanted to have, and the mathematical concepts as approximations to his numerical concepts. So to summarize, both Nauer and Van Wijngaarden did not want to make a science on a particular make of apparatus, IBM, but on the other hand, they did not embrace these two key abstractions either. They were numerical analysts, and they had an alternative. And Van Wijngaarden even had a whole formalism for this, which I will now not go into. It becomes interesting when we now look at the 70s. We have Christopher Strachey, who had changed his view drastically from the 1950s on what programming entails. And he is now considered to be one of the fathers of functional programming. And then we have Dijkstra in that same year, who is countering the way Strachey actually mathematically models computation. Strachey says it is true that our machines can only provide an approximation to these functions, but the discrepancies are generally small. We usually start by ignoring them. It is only after we have devised a program which would be correct if the functions used were the exact mathematical ones that we can start investigating the errors caused by the finite nature of our computer. Just in a word, Strachey embraced both these two abstractions. Well, I don't think you will find many accounts, many models that did this if you would go back in time. So in the 70s, you see people like Strachey who worked closely with Dana Scott to build up formalisms that embrace both these abstractions. Dijkstra did not like that. He said we are considering finite computations only, therefore we can restrict ourselves to processes taking place in a finite state machine. And he attributed the introduction of infinite computations and other self-inflicting pains to the logicians Turing and Scott. To summarize, he did not embrace abstraction AR, that's for sure, but then you could ask yourself, what about that other abstraction HaPoC? Well, then I have to go to his 76 book, The Discipline of Programming, and you will note that in his algo-like mathematical programs in that book, you are able to give arbitrarily large integers as input. So he is accepting this abstraction, but here's the trick. Unlike Davis, unlike Mayer-Ricci, and unlike Strachey, Dijkstra's state does not just resemble the value of a variable, but it's abstractor. It resembles a set of assertions on data, and as a result, he only needs finite states, and that's why he emphasized finite state diagrams. He also had a very different way of looking at the halting problem when you compare that to Minsky or Strachey. He said correctness has to go hand in hand with programming. Correctness proving and programming. I don't know a lot about model checking, but I do know that Emerson was sitting in the same building with Dijkstra in Texas, and he was in the late 70s, or maybe early 80s, maybe that's more accurate. But he was also influenced by Dijkstra's 76 book, which I just referred to. And this is what Emerson says. The industrial success of model checking lies in the fact that several industrial programs can be represented, and now I'm quoting him, at a meaningful level of abstraction by a finite state system. Just again to convey the message that there are different ways on how you can model real industrial computations. You can actually resort to a finite state, a finite mathematical object, and you will not be an exception because there have been prominent computer scientists who have done that before you. What can we take away from this? That the word program acquired very different mathematical meanings during the past decades. That's the pluralism. And as a result, it would be a drastic oversimplification if somebody would now assert that a mathematical program can only be synonymous to a Turing machine. And it would be equally naive to claim that an industrial programming language is best viewed or can solely be studied in terms of a Turing-complete language. If I were to go on talking for another half hour, I would now start to dig into these seminal papers where they actually use the Turing completeness of some industrial programming language like C or VHDL, etc. and then use a lot of mathematics, which by itself is completely correct, but then they project it onto practice and say that there are things you cannot do in practice rather than staying in your mathematical world, like we saw in the first talk with decidability and undecidability of propositional logic, etc. That's just staying in your mathematical world, that's just fine. But there are things happening here which are philosophically probably not entirely correct. Not every model of computation that has been developed complies with these two abstractions. That is what I have shown with a couple of historical case studies. And some computer scientists have preferred not to abstract away finiteness. So, let me put it this way. Peter Nauer and Adrien van Meijgaarden did not abstract away the finiteness of real machines. Dijkstra did abstract away the finiteness of real machines because he embraced that first key abstraction, but he did not abstract away finiteness tout court. He still had finite state diagrams. And then there are people who did abstract away from finiteness, and you go to Turing machines, for example. So only if we do abstract away from finiteness can we conclude, relative to our chosen modeling technique, that specific problems with regard to our chosen technological artifact are unsolvable. How much time do I have?
10 minutes if you want.
Then I would like to show you a debate between Parnas and Chaudhuri in the Communications of the ACM in 2012. The right-hand side here is Chaudhuri, he'll pop up over here, and we have Parnas criticizing this paper. On the other hand, he will also admit that the paper, of course, has added value, that's not the point, but they use a different meaning for the word program. So this was originally published in the POPL community, and then a paper also in the Communications of the ACM. It's about continuity robustness of programs using a lot of mathematics to build very useful software tools. And Parnas says the following: Shadouli et al. Said the most basic reason why software systems can violate continuity is conditional branching. But they ignore the more fundamental cause, namely that program variables have a limited number of states. This is related to, if you like, finite number of states, okay, limited number of states. What exactly does he mean here? Parnas continues, computer representation of real numbers is inexact, and only a finite subset of the integers can be represented exactly. So he's talking about real arithmetic on a real computer. Consequently, in computer arithmetic, equations such as the blue one need not hold and can introduce discontinuity. So Dave Parnas, for him, a program is far more a computer than a mathematical program. He continues, the article ignored the problem by both declaring our reals are infinite precision and not specifying upper and lower bounds for integers. So that article of Shadouli embraces both abstraction AR and HaPoC. These assumptions are common in mathematics. I mean, Parnas has read many of those papers before, but they are not valid for computer programs, not for the programs that Parnas is referring to when he says this. Models, mathematical models, often have properties real mechanisms, which I would call technological artifacts, do not have, and it is possible to verify the correctness of a mathematical model of a program, even if the actual program will fail in the real world when you execute it. This is similar to Brian Temple-Smith's message in 1985. The article's approach is nevertheless useful because attempting to prove a mathematical model of a program correct can still reveal subtle errors which are very useful in practice. Shadouli et al. Reply, from a purely mathematical perspective, any function between discrete spaces is continuous, so all our computer programs are continuous. They're not really communicating. If you keep on wearing those mathematical glasses, and once again, there are many different mathematical glasses, but if you wear those which embrace those two abstractions, a la Strachey and Shadouli, then you can make this statement. Also, our framework extends to programs that operate on values ranging over finite sets. We also have evidence that a robustness analysis can be adopted to this context. What he's saying is he can extend his mathematical framework to introduce a finite condition on the functions that you're modeling, and that's just fine, but that's not what Parnas is saying. Thank you very much.
Thanks, Edgar. So we have some time to take questions.
Yeah, I would like to challenge a little bit the word mathematical, because the view we had of floating point numbers has evolved a lot with time. So it's true that at some point in history it was meaningful to have a distinction between the mathematical reals and the floating point numbers, of which we knew nothing. But then there was a point where mathematicians start looking at this subset of the real lines, this finite subset of the real lines of the numbers we can represent, and start proving theorems about these numbers. After all, they are real numbers like any others. So they had a lot of theorems about approximations, about the possibility to compute one operation exactly or not, different things. So at some point, even studying the set of floating point numbers is mathematics.
Sure. I completely agree with this. I think Adriaan van Wijngaarden would have agreed with that. He wanted to make a science based on, if you like, floating point numbers. Yeah.
Would you have similar situations in physics where you write your physical laws with arbitrary precision, real numbers, and then you do physical experiments and you can only measure your numbers up to a certain number of digits and so on?
Yeah, so first of all, I don't know so much about physics because I'm more a computer scientist, and that's a vexing research question, like to what extent is science similar to physics, to what extent not, etc. But my educated guess is that in physics they have already for a long time been distinguishing between the model and the real thing. And based on what you just said, I think you might agree with this. But in computer science, that distinction between the two is often, not always, but often conflated. And I'm by no means the first one to suggest this. Already in the 80s, you have philosophers of computer science like Brian Smith, and more importantly, well, James Fetzer, and another one I forgot, who have pointed this out, this conflation. So when you say a Turing machine takes 3 seconds to execute, a philosopher will say, you mean, what do you mean? The Turing machine is just symbolic. Of course, you're probably referring to a practical realization of a Turing machine. And you could say that's just a façon de parler, a way of talking, and there's no harm done. But if I were now to continue for 30 minutes, I would show that some computer scientists and some big names have conflated those two ideas and made claims based on solid mathematics, but then in a big context where they project their theory onto practice where it might not completely make sense. Anyway, I'm not, just look at Fetzer's work in 1988 in the communications of the ACM. I mean, Mati Tetre knows this. This was a philosopher of computer science who completely challenged the program verification community, and that's because he was right to some extent. So you got all these hostile remarks, but he was right to some extent, but as a historian I should not choose sides actually.
So you can, as a person.
As a person I can.
Can I, okay, I'll use my time as check. So I agree in general that a specific aspect of computer science is this need to distinguish between the model and the object, if you want. My question, I think, is, it's difficult for me to put it properly, but I think my question is, don't you think that even your way to put it is simplistic? That there is a model and then there is an object?
Oh, great, great. Well,
yeah, so.
No, excellent, because this is why I'm talking to philosophers and reading a lot about philosophy. I don't want to make a philosophical mistake in my arguments. So all I'm trying to just introduce what I need, and that's just that distinction, what you just said, between what also the only distinction Smith makes between the model and the technological artifact. And that's what I see most of these philosophers do. And you're probably right. If I now would dig into Brian Cantwell Smith's later work, which I do not completely understand yet, there might be more distinctions to make than just what I just did. But I don't think that that's going to invalidate the observation that there's conflation here in computer science. And if there is, fine, then we just progress in our understanding. But first we need to realize that there's something going on here.
I mean, on a very simplistic, on a very first approach, you could even make a distinction between the pair composed by the program and its input and the running instance of the program on that input, which are, of course, two different objects. If we are talking a very abstract level.
So there are papers, I might now be mixing names, but I read by HaPoC a paper where they make these distinctions, but to talk to computer scientists, I don't need to go there. I mean, but you're right, it's fascinating to do that. I'm just saying whatever's on my laptop, whether it's executing or just stored or not yet compiled, we don't yet understand what that is, but everything there which I can destroy physically is different from the mathematical models. And probably there's some hardcore philosophers who might even challenge this, but I know that there are people like Fetzer who probably will agree with this only distinction I'm making, but I need to talk to these people at least.
I have a very small question. So, when you say that you know, unsolvability results, you know, that are there for the model do not apply to the you know, implementation of the model, would you go so far as to say that it has no practical relevance whatsoever? And if you don't go as far, what is then the practical relevance of these?
It's exactly what Dave Parnas says, but what Dave Parnas says is it's not because you can prove something in your model that it actually holds in practice. That's what he says, and he gives the example of the arithmetic. I would say it's not because you can prove that something cannot be done according to your model, that does not mean that there will be somebody else, Dijkstra, who models the same computation differently. For him, everything is decidable, and he even talks like that. So, what I'm saying is every model is useful, and a good engineer is going to use different models. And I'm not saying this is useless, by no means. So, if you can model something with a Turing machine and you show it's undecidable, then we should by all means respect this and take that into account when you use that model to work with industrial things.
And in what sense would you take it into account?
Oh, okay, so if I program in C and I'm writing a software tool in which I'm actually interpreting C to be, and looking at it as a Turing complete language, so I'm using some software tool that has made that abstraction. An example is Byron Cook's work in Microsoft, where he has all this useful software technology to check whether a program will halt or not. It is in general an undecidable problem because he's made that abstraction. Then I should not try to now solve something which has been shown to be undecidable with regard to that model. But if I'm Dijkstra, I would model that same thing differently, and then I would also approach the whole decidability thing very differently, and then I have very different problems and very different virtues and vices compared to that other model. That's Smith's point, that different models have different advantages. And in computer science, the tendency is to think that a program has to be a Turing machine. And so a computer virus has to be a Turing machine, that virus paper I referred to. They model programs, viruses, as Turing machines, which is fine, but then they should also acknowledge that there are other ways to model it. Now I realize this is a bit, this is on the peer review, okay? So I realize this is...
I'm not sure I completely understand what you say, because if we have the view that choosing a different model of the same reality, we could get to one conclusion or to the opposite.
They don't contradict each other.
Well, okay. You have one way to model what the program is, for which the handling problem is undecidable, and another for which it is decidable.
No.
If we say that, I think we have to be brave enough and to say that these models are useless. How can they be useful?
No, so I apologize if I gave the impression that I did say that. I still need to find mine. But I know what you're doing. You're looking at all models with computability theoretic glasses, while if you would model a la Dijkstra, don't wear your computability theoretic glasses. And I know, look, let me put it this way. I am at this point not able to probably use the right words. It's like you have a car. You can model a green car as red. There are people who do that. I mean, that's not a contradiction. Whether that's useful, I don't know. But model checking is based on, especially useful for protocols, because these are actually, these kind of applications are inherently finite state. So they use finite state models. But there's no harm done in modeling that with a Turing machine, and that you actually get some serious good insights which you wouldn't have gotten with the other model. So good engineers dealing with embedded software, they use all these different kinds of models or different programming languages. They don't all program in one and the same language, even though many academics, or some academics, would like to have a world, maybe not anymore today, but in the past they would like to have had a world where they were just using their own programming language. That's perhaps not a nice remark.
Okay, so I think that we agree that there are different levels of abstraction at stake. If there are no other questions, oh yes, please.
Okay, so is there any, speculations or discussions on other themes of unpredictability of software behavior, say for instance race conditions, parallelisms, and so on? Didn't get me.
No, sorry, I don't understand. Yeah.
Okay, so you just pick one set of problems that are hard to simulate or to model. Yep. Finity or infinity of integers or float numbers. Correct?
Yeah, I focused on computer arithmetic.
Yeah.
In general, yeah.
Are there any other problems of uncertainty of software behavior?
Well, my guess is I could have perhaps looked at buffer overflow instead of computer arithmetic, and then looked at all these actors. How do they deal with buffer overflow? I'm pretty sure that Dexter would have approached that differently from Strachey, etc. And then we could talk about buffer overflow. And you have the models.
So and your speculation is that a very similar argument would apply even if you will change the focus of your example.
Yeah, this doesn't have to be about computer arithmetic.
You have a wonderful example, which is computer security.
Yeah.
So you can prove that against all attacks in the world, your computer is safe.
I can't do that.
In some models.
I'm not sure that's
and then you have another kind of attacks that are based on the physical properties of the computer, like the power consumption. And this was completely out of your model, so you could not predict, you cannot even speak about it in your model. So whatever you can prove about the security of your system, it's insecure for you.
This line of argument is in fact very similar to the argument that Fetzer does in the paper you mentioned,
but
where he claims, okay, we can do whatever we want with formal correctness, but then X-rays or whatever you want physical properties still endanger the correctness.
So can I just say one more thing? So
yes, and
you're right, and you're both right. So Brian Cantwell-Smith would say, oh, your model didn't deal with power consumption. Maybe you should consider modeling that with another model. Fetzer would say, whatever model you take, or you take 5 models to do your thing, once that your program is running, you've just proven correctness with respect to your model in a formal framework. But once it's embedded in the real world, things can happen. I mean, I don't know, maybe a rock out of space will fall on my laptop, or something, some hardware malfunctioning or whatever. These are things that you don't have any control of anymore. Of course, you could try to model this thing, but you're always going to be limited in what you can do. So, yeah, so Fetzer, this is primarily not been about Fetzer, but you're right, that should be part of the complete big story of the whole analysis.
Okay, so I think it was a very lively discussion. I suggest we thank Edgar for his presentation. So I'm very glad that we are ending up with what seems to me at least a very significant word from people that come from the computer science originally, and the next in line is Gilles. And it seems to me that this suggests that a lot of topics, both in history and philosophy, are still to be discussed. So Gilles is next in line, and
so I don't have slides, but I have a